conduction through cylindrical pipe. Your life, heat conduction through cylindrical pipe, your life is easy when you have flat plate and heat is getting conducted from one surface to another surface. Okay, but if you have cylindrical pipe, circular pipe like this, okay, then how this heat transfer will be going on? What x value or thickness value will be taking? Okay, because R1, R2, okay, R1, R2, if you see, this area is changing. Okay, when area is changing, when you can't use directly the formula whatever you have used for Ka del T by del X, right? So here formula will change. Here formula is this: Q equals minus Ka dt by dr. You have to take differential form because your area is changing. Equals minus Ka, A means area. Which area? This surface area. Okay, so 2 pi r, 2 pi means your perimeter, into L, surface area, because from inside temperature T1 and outside temperature T2, like it is a common circular pipe. Okay, in circular pipe, inside temperature may be higher, outside temperature may be lower. So heat is transferring from inside to outside. So area will be the whole cylindrical surface area. That's why 2 pi rl and dt by dr. Okay, so L equals length of the tube, pipe or tube, whatever you say. Okay, so you have to integrate to get this dt, dr and q, all this. Okay, so T equals T2, T equals T1, dr equals R1, R2, q by 2 pi rl, 2 pi r has gone, so dr by r they have put here because this is a constant term. So T2 minus T1, T2, this is dt, this will be dt. So T2 minus T1 equals q by 2 pi r, 2 pi kl, logarithm of dr by r, log will come, so r2 by r1. Okay, therefore q equals 2 pi kl, 2 pi kl T2 minus T1 divided by logarithm of natural log R2 by R1. Okay. Now Q equals 2 pi L R2 minus R1 K T2 minus T1 R2 minus R1, R2 minus R1 up and down both multiplied, 2 pi denominator and numerator both 2 pi R2 L, 2 pi R1 L. This is logarithmic. So this will give K A2 minus A1 T2 minus T1 divided by R2 minus R1 logarithm of A2 by A1. Okay, now A1, A2 are the inside and outside surface. So Q, okay, now A2 by minus A1 by logarithm of A2 by A1. Okay, inside outside surface area. A1m, they have taken this notation, and xw equals R2 minus R1. Okay, this will give Q equals K A M 1m T2 minus T1 R2 minus R1 or minus K A 1m T2 minus T1 by Rw. Okay. and here R equals x m by k 1 a 1 m. Now R equals R1 plus R2. So if I have two pipes, I'll be giving different shading so that there will be no confusion. Okay, so T1, T2, T3, and so R equals R1 plus R2 equals X W1 K 1 A1 M1 plus X W2 K 2 A2 M2. Okay, X W1 equals R2 minus R1 equals then X W2 equals R3 minus R2. So A1 M1 equals A2 minus A1 logarithm of A2 minus A1 not minus A2 divide equals 2 pi R2 minus R1 L by logarithm of R2 by R1. A1 M2 2 pi R3 minus R2 L divided by logarithm of R3 by R2. Okay, the rate of heat transfer will be Q. Rate of heat transfer is Q equals T1 minus T3 divided by R equals T1 minus T2 by R1 equals T3 by minus T2 by R2, from which the interface temperature T2 can be evaluated. So, heat conduction through a wall. You have a wall. Okay. Now, what will happen? There will be one boundary layer both side. Okay. And through boundary layer also there is some gradient will be created. T, T2, T1. Okay. And this flow rate will be, heat flow rate is Q. So, R equals R1 resistance left side plus resistance of the metal plus resistance of the other side because of boundary layer. So, the formula will be like 1 by H1A plus 1 by X by K plus 1 by H2A. The same area you are using. Q equals TH minus T cold, T hot minus T cold divided by R. So, this will be like TH minus T cold 1 by H1A plus X by Ka plus 1 by H2A equals UA TH minus TC. So, U is called overall heat transfer coefficient. U is called overall HT coefficient. Okay. So, 1 by UA, therefore, 1 by UA equals 1 by H1 plus X by K plus 1 by H2. So, hot fluid through a pipe. Now, I have one pipe. Again here inner one boundary layer created and outside also one boundary layer created. Okay, and this is my pipe. I am shading the pipe so that it will be clear. Okay. Now small r, capital maybe R1 R2. I can make. So Q equals TH minus T cold R1 plus R2 plus R3 equals TH minus T cold divided by 1 by H1A plus XW KW AW plus 1 by HOAO. Okay. So O means outside, HI or inside. Okay. I can put. So Q equals UA. This is hot fluid inside cylinder. Hot fluid inside cylinder. So outside temperature is lower, inside temperature is higher. TH minus TC. So 1 by UOAO equals 1 by H1A1 plus XW KW A1M plus 1 by HOAO. H1 or HI I can write. So if XW is small, so AO, A1M, AI all equal. So 1 by UO equals 1 by HI plus AXW KW plus 1 by HW. So this is taken from PK-NOC book. So if anything goes wrong, please go through the book. Non-dimensional numbers. So I already discussed non-dimensional numbers like Reynolds number, Prandtl number, Nusselt number. There will be some other numbers like Grashof number, and many other numbers are there. So basically for our convective heat transfer coefficient, we will be using this Reynolds number, Prandtl number, Nusselt number. Okay, Reynolds number is very common actually for any fluid flow we are using. So the formula is U d rho by mu. So nu is kinetic viscosity, its formula is mu by rho, and unit also you should remember, meter square per second. Okay, Reynolds number less than 2000 is called laminar, and more than 2000 okay, about then it will be turbulent. Okay, why laminar and turbulent will be required? When turbulent is there, so we will have more heat transfer coefficient because of forced convection. Nusselt number, already I have given formula, HD by K, Prandtl number mu Cp by K, and H equals function of diameter, viscosity, rho, mu, K, Cp. Okay, and Nusselt number and Prandtl number, many formula may be there, but one formula is this, like N Nusselt number equals 0.023, Reynolds number power 0.8, Prandtl number power n. So n equals 0.4 for heated fluid, and equals 0.3 when fluid is cooled. Okay. Now you see the simpler problem, two plates of equal thickness, here one plate, another plate is here, cross section area and cross section area from a composite heated medium, thermal conductivity K is 2K, area you can assume A, the effective thermal conductivity of the composite is, so you can see the formula, the steady state heat transfer total R1 plus R2. So R T by Ka, area and thickness equal. Okay, R total 2 Tk effective. So R1 T by K, R2 T by 2K. So therefore T by K plus T by 2K equals 3T by 2K. So 2T by K effective. So therefore K effective is 4 by 3. Okay, if you see add all this, then it will be coming 4 by 3 K. Another problem is that circular tube transporting hot fluid, given data is given, circular tube, hot fluid is transporting, so outer diameter 0.5 meter, inner temperature T, inner temperature 80, outer temperature 25 degree, and radius 0.4, this is 0.5, and per meter length of the tube heat transfer. So, Q value already you have to use the formula 2 pi L Ti minus To log Rho by Ri. So, if you put directly the formula the values from the formula, then you can get directly 15487 watt per meter. Okay.